combination reactions and decompositions and all of those. It's totally not where I was going with this question, but it is a valid answer. So big topics from first semester. This is kind of my breakdown of what I see from first semester that you should remember. We get structural effects. Right? This is really unit 1. This is orbitals. So hybridization theory, molecular orbital theory. Right? Everybody hates molecular orbital theory pretty much universally. It is insanely powerful, but it is so convoluted and confusing that most people don't spend the time to figure it out. They just kind of gloss over it and memorize reagents. Okay? That's fine. Okay? This is also where we get stereochemical effects and sterics as a structural thing. Stereochemistry will become somewhat important within the first part, and then it kind of disappears from the curriculum when we move into carbonyl chemistry. Electronic effects, resonance and electronegativity. Right? In first semester, I always start off with the answer to all questions is resonance, and it's always a horrible way to start because in first semester the answer is not resonance typically because we haven't done enough chemistry to talk about resonance. Okay? But I always remember it because usually I'm teaching first semester after I finish talking about second semester, and the answer to virtually every question in second semester is resonance. Okay? So if you're trying to figure out why something worked, it's probably because you didn't draw a resonance structure that was better than the one you started from. Right? So resonance becomes really important. Electronegativity helps dictate where your resonance structures are going to move. Right? The next stage down is your strength of acid, base, electrophile, or nucleophile. Right? This is kind of an important one for definitions. Right? When I say acid and base, not my students, former students, that is. Okay, so that means anybody that wasn't my former student, so you're good. You guys. I see you because I don't know you. Okay? When I talk about acid and base, what am I talking about? Right? We might say Lewis. Right? Lewis is a phenomenal definition for acids and bases. The problem that I have with the Lewis acid and base definition, it is way too broad. Right? Because an electrophile is a Lewis acid. So when I say acid, if I'm saying a Lewis acid, then I'm confusing it with an electrophile. Right? So I don't want that confusion. So when I say acid and base, I'm not talking about Lewis. I'm talking very specifically about Bronsted-Lowry. That's the transfer of hydrogens. Okay? And in particular, hydrogen ions, okay? The cation. When we're talking about any other atom being transferred around, that's our electrophile nucleophile. I don't use Lewis acid, Lewis base there because, again, Lewis acid and Lewis base applies to Bronsted-Lowry. Right? The electrophile and nucleophile is now only about the transfer of electrons, okay, where it is not hydrogen involved. Okay, whereas our acids and bases are hydrogen ion involved. Right? It's just a simple way to delineate so I don't have to go through and constantly, well, this is a Bronsted-Lowry acid. I can just say acid, and we're done. Right? That is not standard. Most people refer, or most organic chemists refer to acids and bases as Lewis. Right? Again, it's just kind of a structural thing within my brain to help quickly explain things because I'm already wordy enough, clearly. When we look at ranking strengths of acids and bases, okay, and the activity of electrophiles and nucleophiles, it comes down to 6 rules, and really only 5 that we'll ever have to largely deal with. The 6th one is fairly rare. Right? The first thing we're going to evaluate is charge. Okay? Then we'll evaluate the atom size. So what atom is holding said charge? Is it big? Is it small? Okay? What about the atom electronegativity? Right? Is there a molecular effect like resonance? Is there a molecular effect like inductive effects? Right? And if none of those rules worked, then I can worry about hybridization. Right? They are in a numerical order for a reason. Why? Because that's how it's important. I'm not going to evaluate the reactivity of a nucleophile by first jumping to the electronegativity of the atom present in the molecule. I can have a fluorine in a molecule, but it's not charged. If it's not charged, it's not my reactive site. The charge is where I want to look. Okay, so this is all about finding the most reactive place and comparing it to the most reactive place somewhere else. You follow through this rule set. Charge comes first, followed by size, followed by electronegativity. The most common swap, size and electronegativity. We almost always evaluate electronegativity first. That's wrong. Evaluate size. Okay? We could run silly examples with it, but I don't have pictures. Like if I came running at you versus the world's strongest, tiniest man, you would probably freak out a little bit more about me, at least at first, until you saw how strong the guy was, because he's really strong, right? But there's enough critical mass behind me that if I ran into you, it doesn't really matter how strong I am. I'm probably going to hurt you because there's more mass. Okay? So, he exists. He's actually kind of cool. The next thing is you'll notice that I've got these lined up kind of side by side. The atomic effect of size gets repeated as a molecular effect of resonance. Okay? Size is where the electrons around an atom. Well, if there's a larger atom, those electrons become more stable. Okay? What happens if I move to resonance? Well, resonance is how electrons move. If there's more resonance, that means there's more size or space for the electrons to exist. It becomes more stable. So resonance is really just the molecular effect of size, but at a molecule scale. Same deal with the inductive effect. Induction is just the ability of an atom to withdraw electrons. You mean like electronegativity? Yes, exactly like that. But in the molecular scale, not at the atomic scale. What is hybridization? Add molecular bonding theory stuff, which everybody ignores and hates, and then throw it back up to the atom effects. Okay? And really it's electronegativity. Okay? So that's usually thrown in as a last-ditch effort. There are other things that you could evaluate. We typically don't have to, so don't worry about them, unless you have to cross that bridge. You won't. Okay? Remember, we answered that question already when nobody rose their hand during the synthetic chemist argument. Okay? So we don't have to deal with it. The next part is reactions versus mechanisms. Reactions are the what, right? And that's the specific reagents. Ochem 2 is full of reactions. Virtually everything you see is a reaction with a new reagent that tells you what happens under those circumstances. You are responsible for those. Okay? The mechanism is the how. How did those pieces come together to make that product? Okay? They're similar concepts, but they have different applicability. If I understand mechanisms, I can look at a reaction I know nothing about and predict what might happen. But if I look only at reactants and I see a new reactant that I haven't seen, what can I do? Nothing. I have no fundamental basis on which to make an educated guess. Okay? The mechanism allows me to predict things that I haven't seen. Reactions allows me to predict things that I can only see or that I have seen in the past. Not only that I've seen in the past and I bothered to memorize. Okay? Both of which I'm very bad at. Okay? So I want to focus primarily on the mechanism. Both questions get asked in varying ways. Okay? So, what are the reactions? Acid, base, substitution, elimination, addition, and radical. Okay, interestingly enough, that would be exactly 5 reactions. That was the answer I was fishing for earlier. Okay? If you didn't get it, don't worry about it. It's not a big deal. Right? Those would be the reactions. Are there mechanisms based on those? Yeah, well, the acid-base. How many acid-base mechanisms are there? One. That's about it, right? Yeah. Okay. Substitution. We've seen at least 2, right? SN1 and SN2. Creative names. Elimination? E1, E2. Addition? I fully expect my students to be like, what the? I don't remember how many. There's tons of kind of basic mechanisms that run through that. They aren't as clearly labeled as the substitution and elimination. The addition become quite a big mess. Okay? They're almost always involving some kind of cyclic intermediate, and it is very typically based off of reagents.
Is he? But I remember this last time.
Uh-huh.
Markovnikov.
So Markovnikov is not an elimination mechanism. It is an observation of a result.
What's anti-Markovnikov?
It's an observation of a result. It's opposite result. Yeah. Where's my right hand? Seriously? Can no one answer that?
Do you mean like
This is my right hand. Yeah. Just give me some. Where's my right hand?
right there? On the right side of your body?
Right side of my body. Okay. Where is it?
In the air?
Right side of my body. How about here?
Confused.
Oh, Markovnikov said, guess where Mike's right hand is going to be? The right side of his body.
Oh. I remember.
Is it on the right side of my body anymore?
I remember now.
Well, no, it's not. So now we'll call it anti-Markovnikov. Or somebody else came through and said, Hoffman. Why did somebody else get to attach their name to it? How often would we expect my right hand to be on the not right-hand side of my body? Okay? It doesn't happen very often. I would have to stretch across. Okay? Markovnikov and Hoffman are observations of that result. Why do you see my right hand on the right-hand side of my body? Because it's attached to the right-hand side of my body. Okay? The observation says nothing about where it's attached. It just says it's there. Oh, because I see it there, I'm going to say it's there. Right? That is an amazing thing to attach your name to. Like, right? You're just like, we now have Mike's rule, because his hand is on the right-hand side of his body, and I'm going to make every student hereafter memorize Mike's rule. That Mike's hand is going to be on the right-hand side of his body. Oh, look, it's applicable to other systems. Everybody's right hand is typically on the right-hand side of their body. Amazing. I get credit for that. Now, whenever you're walking down the street and you see somebody with the right-hand side on their right hand on the right-hand side of their body, you can be like, you're following Mike's rule. Yes. Right? And I become famous. Right? We find that utterly absurd because we have the extra tools to recognize that the right hand will almost always be on the right-hand side of the body because it's freaking attached. When did Markovnikov make that observation? My students should be able to answer that, relatively. Before evidence of electrons. Okay? We had no concept of bonding, and Markovnikov was able to say that hydrogen's always going to be right there. That's where it's going to be. Didn't know anything about how it's connected, but could predict where it's going to show up. That's pretty phenomenal. Okay, that is cool. That we still memorize it after the fact that we know something about electrons, not so cool. My personal opinion. Okay? So there are rules like that. That would go to a memorization. You'll see me yell and scream about them, as I'm sure the rest of the class can tell you about. They're fine to memorize. You just realize you need to be cautious that you always memorize them correctly. That's the problem with memorization. Does that make sense? Okay. Radicals, we really get two types: substitution, radical substitution, and radical addition. Okay. What happens if I combine an elimination with an addition? I have a new mechanism. That new mechanism is now called an elimination addition. Phenomenal. That's now an entire whole new unit. Unit number 3. 2. 2. 3. I like 3. Okay? So that's where we'll go ahead and end for today. A quick little review so you got to see things. One of the things I'll throw up here was a bunch of white lines. Okay? Think about how you would describe each of those reactions and an example reaction. Just trying to think back to what you learned in first semester, piece those things together.